So hello, welcome back to another episode in CSC 280, the Introduction to Cybersecurity. In the previous video we talked about domain names and how we can translate domain names to IP addresses. What we'll do today is take a closer look at how those IP addresses form networks and how we can exchange information between different networks that are connected to the internet. Again, just like in the previous video, I am going to take a few shortcuts. Technical details are always more specific than what I can do in a 15-minute video, but the big concepts that I'm trying to convey stand and will apply nevertheless. This applies to IP version 4 as well as it does to IP version 6. So having said that, let's get going. Let's try resolving a few host names. Turns out, if I resolve the host name adelphi.edu to its IP address, I end up with 192.147.12.33. That's what it is. If I resolve login.adelphi.edu, I get the number 192.147.12.23. Panther.adelphi.edu is 192.147.12.4. Class 192.147.12.234. Intranet.adelphi.edu 192.147.12.12. Now, if you're paying attention to what these IP addresses look like, you'll start seeing a pattern in them. All of them start with 192.147.12. And that's not by accident. In terms of the internet, if I talk about a network and what it really is to be a network, it's really nothing more than a continuous range of IP addresses, uninterrupted. So anything, for example, starting with 192.147.12. something is all part of the same network. If you look at those IP addresses, they're really not just numbers. They're actually a combination of 4 numbers, separated by periods. Each of those positions, the first position, the second, the third, and the fourth, can hold values between 0 and 255. So I could, for example, have an IP address 1.2.3.4. Any of those 4 numbers fits between 0 and 255, and therefore it's valid. I could have a number, an IP address, for example, 192.168.1.100. Again, all of those 4 numbers are part of the same, of the range 0 through 255, and therefore these are potentially valid IP addresses. If I would see things like 900.212.317.516, those would not be IP addresses because I cannot exceed that value of 255. Knowing that we have 4 positions and each position can be at most 256 possible combinations, and I should actually update that in the slide, it ends up that we can have at most 4 billion unique IP addresses on the IP version 4 addressing scheme. One of the key differences between IP version 4 and IP version 6 is that an IPv6 address is much longer. It contains more digits, and as a result I can have more possible combinations. IP version 4 addresses are scarce. There are not enough addresses for everyone who would want one. Now, we found ways to deal with it, and in practice the limit of IPv4 isn't so much of a major limitation that it becomes problematic. IP version 6 has the ability to assign 2 to the power of 128 possible IP addresses, which is a huge, mind-boggling number, more than we'll for the time being need. But then again, that's what we thought when we implemented IP version 4 as well. IPv4 addresses at this point are scarce. It's hard to get a new one. But again, we really don't need them. We have found ways to work around it. And maybe they're not always as ideal as they should be, but they do work. Now, let's take a closer look. Each of those positions can have a number between 0 and 255. In other words, 2 to the power of 8 possible addresses. And that's 8 bits, and 8 bits is a byte. The number 256 to any computer science major should be really familiar, because that is the number that 1 byte can hold unsigned. And so it means that if the first 3 digits of those number combinations are fixed in my IP address, like we saw when we were looking at 192.147. etc., or when we're looking at the addresses we might get at our home routers, 192.168.1 or .0, all of those, the first 3 numbers are fixed. And that means I can only assign the last digit, those up 0 through 255, to computers on my network. And there's actually a couple of reserved numbers in there, but for now let's ignore that part. The key number there to recognize is the first 3 positions in that IP version 4 address might be fixed and cannot change. If that's the case, we say that the first 3 digits, or in other words the first 3 bytes, or in other words the first 24 bits are part of the network, and the last 8 bits are then part for the hosts. So we want to write that. We have a shorthand for that. Let's say that we have the IP address range 192.168.12.0 all the way up to 192.168.12.255. The first 3 positions are fixed. In other words, the first 3 bytes are fixed. In other words, the first 24 bits are fixed. And that means that I can write this as 192.168.12.0/24. That /24 basically says the first 24 bits of this network address are fixed. You can only use the last 8. We do the same thing. For example, if we would write an IP address range of 10.17.0.0 all the way up to 10.17.255.255. Now the first 3 are not fixed right now. Only the first 2 are fixed. So the first 2 positions are fixed. That means the first 2 bytes are fixed. That means the first 16 bits are fixed. And I can write this as 10.17.0.0/16. That numbering is known as the CIDR notation. That is how we write down a network. And so to figure out how many computers are on a network, you would take 32 minus the number that is shown after the slash. In this case, for example, if we look at the 192.168.12.0/24, 32 minus 24 is 8. That means that I have 2 to the power of 8 possible IP addresses on my network, and that's 256. So that's what that notation means if you ever see that. Now, at this point we know that a computer has an IP address that it needs to connect to the network. And we know that a continuous range of IP addresses is also known as a network. So the question now becomes, if I have 2 computers on the network, they can exchange information by IP address. If I send something from 192.168.12.1 to 192.168.12.2, it'll just get there, magic. That makes sense because they're all connected to the same network. But why does it work if they're connected to different networks as well? In other words, if I'm at home and I'm going to load a video from YouTube that is linked from Moodle at Adelphi's network, kind of what you're doing right now, I'm already talking about at least 3 different distinct networks. There's actually more than that if you really think about it. I have my home network. Then I have my internet service provider's network. Then I have Adelphi's network. And then I have Google's network on which YouTube is hosted. How does that work? How can I have these 4 networks and for whatever reason they still are able to exchange information? That, of course, is what the internet gives us. This slide here is a very much simplified representation of that. But basically what we see in the top left is someone who is at home on their laptop and connects wirelessly to a Wi-Fi router in your house. That is your home network. That is a network as well. You connect, for example, to Optimum at home. So now you have your home network and the Optimum network, and they are connected. Now Optimum doesn't necessarily connect directly to Adelphi, and Optimum doesn't necessarily connect directly, for example, to Moodle or to YouTube or wherever. Optimum may have its own internet service providers, and so they could be connected to that. Just like Adelphi has a bunch of networks on campus, but Adelphi also does not connect directly to the internet. Adelphi connects to our internet service providers. And how those internet service providers interconnect themselves, that's sometimes known as the internet backbone. That's where it becomes interesting. So in our case, when we start looking at how can I talk to each other, I have to talk to my Wi-Fi router. My Wi-Fi router has to, that's the little device there. So let's see, there, those are routers. So my Wi-Fi router talks to the Optimum router. The Optimum router talks to the internet backbone. The internet backbone talks to Adelphi. Adelphi talks to Moodle. And then back the other way around. Now I go download from Moodle. So my computer at home talks to my home router. My home router talks to Optimum. The Optimum router talks to the backbone. The backbone talks to Google, and Google talks to YouTube. It is the router, those devices that I'm depicting here as these blue disks, that make that possible. The router connects 2 or more networks, and it allows data to move between those networks. It also means that if you do not have a router, you cannot exchange information that goes off a network or onto another network. The router is that device that connects 2 networks together, or more networks, and allows information to exchange between them. Now, how they find each other is difficult. There's this whole thing called BGP, for example, that announces basically a, let's call it a real-time map of the internet, which shows you what the shortest route would be to get from A to B. For this class, that is a step too far. For that, you need a real networking class. Now, there are security implications. BGP is another one of those trust-based protocols. So yeah, of course, stuff can go wrong there, and sometimes it does. But it does mean that we have to be somewhat aware of that. Now, let's take a slightly more in-depth look at this. Let's say that I am at Adelphi. Adelphi actually has 4 public networks, IP address ranges, 192.100.something.something, 192.160.something.something. The numbers are on the slides. It's really not that important what they are. But what it does mean is that Adelphi constantly tells the world, anyone and anything connected to the internet, hey, if you are looking for 192.147.12.4, I've got it. Come to me. Right? And as soon as we announce that to the internet, in principle, all routers on the internet can figure out where we are and what IP addresses we can serve. Now look at this picture more closely, and you might see that Adelphi's network now is connected to 2 different ISPs, which is true in the real world. Adelphi doesn't use just one internet service provider, we use multiple ones. For a couple of reasons. The most important one being, well, if one fails, at least we have another one left over that we can go on to. There's a couple of other reasons as well, but we do it primarily for redundancy. But it also means that we can't really tell 2 of those routers, hey, if you're looking for Adelphi, come here, because now someone would have to choose which one am I going to pick. Now they could pick one at random, or they could pick one that's closer to them. All of that is actually happening on the inside of the internet. That's how routers work. That's how they figure out where to go. But in basically the other way around is also, let's say that I am looking for YouTube, and I think the YouTube, I can't really read it, is 172.217.0.0/16. And that is when I looked this up, when I was recording this video. Tomorrow it could be different. You could be getting a different answer as well, based on where you are in the world, or maybe based on what Google decides to do. All of this stuff is highly dynamic. It doesn't mean that what it is now will stay that way. But at that point I have to go to my router and I'm gonna say, hey, that's not one of my own networks. So I'm gonna say, router, I have network traffic. It needs to go to that 172.217 network. Make it work. And so the router that we hand this off to might say, well, I don't necessarily know where that router is, but I know the networks I can connect to, and I have my default route, which basically says I don't have a direct relationship with this IP address, but I'm just going to hand it off upstream and hopefully they know. It's almost like you get to an area where you've never been before, no cell phone coverage, and you forgot your GPS at home. So how do you find the street address? Well, you go to the first random person on the street, or you stop in at the 7-Eleven or a gas station and you say, hey, I'm looking for, I don't know, South Avenue. And they go, I have no idea what South Avenue is, but you know what? Go 2 miles over and then at the local bar, ask again. So at least they're sending you in the right direction. And then as you get closer to your destination, hopefully you get correct directions, people will become more certain. For example, you might end up at the beginning of South Avenue. It could be South Avenue is this really long street, and you say, I'm looking for 95 South Avenue. And the local knowledge might tell you, well, I found South Avenue, but now you need to go 3 blocks down and then on the other side of the street. And so the closer you get to your destination, the more specific the answer you will get. And that is the general goal of internet routing as well. If I don't know where to send a network packet, I'm just going to go throw it in the big bucket and hope that someone picks it up from there. And then when they move it closer to their destination, I'm going to do it again. And then I'm going to do that again. So as my network traffic traverses the internet, or in other words, as I hop from one router to the next, I actually carve myself out a little pathway across the internet that brings me closer to my destination. And then, of course, if I get a response, it goes all back in the other direction as well. Routers are the things that make network traffic move. Routers connect different networks, different IP address ranges, and by moving your network packet from your computer to the closest router that you have, and then from that router to maybe the default route, another default, eventually until its destination, that's how the internet works. But it also means that between you and me, there could be a whole lot of different networks. And I don't control those networks, neither do you. And that means that you're traversing network traffic through potentially untrusted networks. Networks that you might not even know. It could very well be that you're trying to load a web page, for example, bbc.co.uk, which is in the United Kingdom. It would not be unheard of for that network traffic first to go to, say, Berlin, from Berlin to Madrid, and from Madrid to the UK. It's not the fastest route, it's not the most direct route, but it might be the only route. And you just don't know, but what's better is you don't care. Because the internet is magic, and magic happens very easily. What we have to keep in mind, though, is that from a security perspective, the things that we don't see and that we don't know about, we have to be wary about. And that means that if we start dealing with network traffic that goes across the open internet, we have to be really careful about what network traffic we trust and what network traffic we don't trust. There's a whole bunch of things we can do to get more insight into how that works. And that is actually using some common diagnostic tools that are built into most modern operating systems. That is the topic of the next video.